Hello, this is Mrs. Taylor, and I'm going to go over the different transformations that you can have of a parent function. These definitions and graphics and things are out of your textbook, the Glencoe Algebra 2 textbook. So first let's start talking about what a parent function is. So according to your textbook, it says a family of graphs is a group of graphs that display one or more similar characteristics. The parent graph, which is the graph of the parent function, is the simplest of the graphs in a family. This is the graph that is transformed to create other members in a family of graphs. So our parent function is the simplest of the graphs in a family. So basically we start with that function and then we transform it in some way to create the other members in the family of graphs. So some examples of parent functions. The absolute value function has a parent function which is just y equals the absolute value of x. That's the simplest form of this function. So it's the parent function. The domain is the set of all real numbers, so no matter what x value you put in, you get a defined y value. And then the range is the set of real numbers greater than or equal to 0. So all your y's for this parent function, y equals the absolute value of x, all the y's will be positive. So that's an example of a parent function. Other parent functions include what we call the identity function. It's called the identity function because it's the equation y equals x, and so y and x equal the same thing, so it's the identity. Its appearance doesn't change. The identity function, y equals x, is a parent function because it's the simplest form of that function. And its domain and range are all real numbers. So it will continue infinitely to the left and to the right and continue to travel up and down. Another parent function is y equals x squared. It's a quadratic function. It is the simplest form of quadratic functions. It is the shape of the graph is called a parabola. So let me spell that out for you. P-A-R-A-B-O-L-A. And the domain of a parabola is the set of all real numbers. So it will continue to expand infinitely to the left and to the right, so that's domain. And then the range, because it's x squared, when you square a number, it will always be positive because a negative times a negative is a positive, and a positive times a positive is a positive. So our domain is all real numbers, but our range is the set of real numbers greater than or equal to 0. So this is the parent function of quadratics, which is y equals x squared. So those are some examples of parent functions. Let's talk about the transformations. So there are some transformations that you should be familiar with from geometry. First one is a translation, which moves a figure up, down, left, or right. So it's a slide up, down, left, or right. Let's look at an example to really understand how this relates to us in Algebra 2. It says describe the translation in y equals the absolute value of x plus 2, then graph the function. So what we learned in our books already is that this plus 2 is in the k's place. And what we learned is that k controls your vertical movement, so up or down. So if it's plus 2, it's up 2 units. And so they want us to graph the function. So this would be a translation up 2 units. And then if I graph it, well, this is why the parent functions are so important. So I know that the parent function, y equals the absolute value of x, is centered here at the origin 0, 0. So its vertex starts here. Well, according to this equation, I need to translate up 2 units. So I take that vertex that starts here and I move up 2 units. That's my new vertex. That's the only thing that changed. So we know that the slope on the left of the absolute value parent function is -1, and the slope on the right is +1. If we look at it, it goes up 1 over 1, up 1 over 1, up 1 over 1. And so we don't have anything in our equation here that affects that slope. So I'm going to use the same slope. So I'm going to go up 1 over 1, up 1 over 1. And then the same thing on the left side because it's symmetric. And then I will just create roughly, my V. Sorry, this is sloppy. I'm trying to use the slate. I'll just fix it up a little bit. So this would be the sketch of my graph of this equation, which is an absolute value function that's been translated up 2 units. The other type of transformation that we are going to talk about is a reflection. It is a flip over a line called the line of reflection. So what we learn in our booklets is that if we have a negative outside of the absolute value here, this is in the A's place in our general form of an absolute value equation. If it's negative, it's a reflection. There's nothing else in the H or the K place, so our vertex is still centered at 0, 0 like our parent function. It's just flipped, it's reflected. So when I sketch that graph, remember our vertex has not changed, so it's still at 0, 0. And instead of going up 1 over 1, I'm going to go down 1 over 1 to show that it's reflected. It flipped over the x-axis. So down 1 over 1. And then on the left side, same thing, down 1 over 1, down 1 over 1. And now I have a reflected absolute value graph, a flip, roughly. This is really messy. All right, the last transformation is a dilation. So a dilation shrinks or enlarges a figure proportionally. That's something you should know from geometry. When the variable is a linear parent function, when the variable in a linear parent function is multiplied by a non-zero number, the slope of the graph changes. So this is the A's place in the absolute value functions we learned about in our booklet. So when a nonlinear parent function is multiplied by a non-zero number, the function is stretched or compressed vertically. So remember in our booklet, stretched meant the V in the absolute value graph got more narrow, and compressed means that it got more wide. It's like it was pressed down. Coefficients greater than 1 cause the graph to be stretched. Remember with the absolute value it was more narrow. And then coefficients between 0 and 1, so in other words your fractions, cause the graph to be compressed vertically. So that means it's widened. So let's look at an example of that. And for that I'm going to use the calculator. Just to give an example of how you can use your calculator to analyze these as well. So we want to see what kind of well, let me restate that. We want to see what a dilation does. So let's work with absolute value since that's what we've been using. And I want my parent function first to compare it to. So you go to the y equals screen, you want absolute value, so you go to math, and then you want to go over to number, and the first option is absolute, so you hit enter. And the first one we're going to look at is the parent function, which is absolute value of x. Okay? And then let's pick one where it is a coefficient greater than 1. So my next one, a number greater than 1, let's go with 5. And then I need to get the absolute value notation again, and x. So now I have a coefficient greater than 1. And if I want to graph that in a standard window, which is negative 10 to 10, I go to zoom, z standard, which is option 6. There's my original, my parent function, and then the more narrow graph is my dilated parent function, which is more narrow, it's a stretch. And then if I wanted to compare those to what happens when my coefficient is between 0 and 1, so we need a fraction between 0 and 1. How about 3/4? So to get 3/4, I do parentheses 3 divided by 4, and then get your absolute value notation and x, and then let's graph that one. So as you can see, this line here is your compressed function. It's like it's being pushed down, it's compressed, it's flattening out. And so if you weren't sure which line represented which function, if you press trace, you can see wherever the cursor is, and it's kind of hard to tell there, so I'm going to move over to the right. move my cursor, and I can see that this middle line is the absolute value of x. If I hit the up arrow, it toggles to this line, which is 3/4 the absolute value of x. And then if I hit up again, I get the more narrow line, which is hard to tell with the, there it is. So this more narrow line is the one with 5 absolute value of x. So that's just a little comparison of the dilations. So the three that we are learning about are translations, reflections, and dilations. And those are the three that you should have seen in our first few pages of our booklet when exploring absolute value.